Welcome, Honors Algebra 2 students. We are on page 212 of your student journals. This is Ms. Fellon, and we are looking at lesson 7.5, which is all about solving. So one of the things we're going to talk about in terms of how to solve a rational equation, one of the methods is cross-multiplying. And so remember, what I want you to remember about that is we've done cross-multiplying a lot in various other units, but we only use it with a proportion. So in other words, you have to have a fraction equals another fraction, right? And so then you cross-multiply and solve. And so that's what I kind of want you to remember about this whole, about using that method. So let me give you an example of a scenario in which you would use cross-multiplication. So let's do 2 over x plus 2 equals 10 over 3x plus 2. Notice, fraction equals a fraction, right? So there's nothing else going on here. There's no other terms. This is now when you can cross-multiply. So you would get 2 times 3x plus 2 equals 10 times x plus 2. Now, to be honest with you, what a lot of people do here is they go ahead and distribute. If 2 and 10, I always find it easier to go ahead and divide both sides by 2 since those are divisible. That way it's a little less numbers to be dealing with. So I just divided both sides by 2. Now I'm going to go ahead and distribute and solve for x. So I'm going to go ahead and subtract 3x. I'm going to subtract 10. And I get x to equal -4. Here's the thing about, and this happens as you notice with a lot of functions, we have to be careful for extraneous solutions. And so with a rational function, remember what happens with an extraneous solution. And think back to our graphs, right? So on our graphs, we have lots of those parts where our function is undefined, right? So we might have these asymptotes in there. Any place those asymptotes exist is going to be a part of your graph that's undefined. So an extraneous solution, which is algebraically kind of like the same thing as having an asymptote, an extraneous solution will occur only if this value here causes a 0 on the denominator of my fraction. So like in other words, 2 divided by 0 would be an undefined answer, right? And 10 divided by 0. So does -4 cause this denominator to be 0? Well, obviously it doesn't, because this gives me -2. Excuse me. And this would give me like -10. So anyway, on those ones, this is actually a fine example. So this is a fine answer because it does not have, it's not extraneous because it does not cause my denominators to be 0. All right, another way we're going to solve is, what if we don't have a proportion, right? So what if we have just, I don't know, a normal equation that might have a couple different terms? So let me show you a couple examples in which we can do, or how I would solve if we had a non-proportion problem. All right, so this is a rational equation. Relatively easy. There's nothing too fancy going on here. Because to be honest with you, my first rule of thumb is, as you probably know, would probably guess, is to go ahead and factor everything that's involved. Well, in this particular problem, we don't really have anything to factor, so we can kind of skip that step. What I look for next, and I do this the same way as I kind of do the complex fractions. I want to get rid of those fractions. So what I do is I look for a common denominator between all of my denominators. So 2x and x, a common denominator between all three of those would be 2x. And so what I'm going to do is I'm going to scale up these fractions. I'm going to multiply 3 over x by 2x, 5 halves by 2x, and -12 over x by 2x. And so what that'll do is get rid of all my fractions. And that way I'm not dealing with having to find common denominators or anything fancy like that. So 3 over x times 2x, you can think of it as 2x over 1. The x's would cancel and you're left with 6. 5 over 2 times 2x, the 2's would cancel and you're left with 5x. And then -12 over x, the x's would cancel and you're left with -24. Notice that that's a much easier now problem to solve, rather than trying to find common denominators and then add these together and then cross multiply. Now, it's not wrong to do it that way. It's just I feel like this is a little bit quicker. So I'm going to go ahead and subtract 6 from both sides and divide by 5. Again, check for extraneous solutions. So up here, the only values that would cause this to be extraneous would be 0, right? So what values of x cause my denominator to be 0? And that would be 0. So as long as I don't have x equals 0, I'm good to go. And so again, your extraneous solutions are going to be anywhere you have your vertical asymptotes. Let's do another example. So let's do 1 minus 2 over x minus 4 equals 4 over x. Same deal here. What we're going to do is we're going to look at all of our denominators. So I'm going to write 1 underneath that one. So I have 1, x minus 4, and x. So the common denominator would be x minus 4 and x. So I'm going to scale all of my fractions up by x times x minus 4. So I'm just multiplying by 1 here. So I just get x times x minus 4 minus, if I multiply this fraction, the x minus 4's cancel out and I'm left with 2x. And on this one, the x's would cancel out and I'm left with 4 times x minus 4. And so on this one, what we're doing is we're going to go ahead and now just solve for x. So I get x squared minus 4x minus 2x equals 4x minus 16. Notice that it's quadratic, so let's go ahead and set it equal to 0. So I get, this is negative 6, and if I subtract 4, that's negative 10x, and then I'm going to add 16. So I'm going to set everything equal to 0 here. This is a trinomial. Let's go ahead and factor it. So I get x minus 8 and x minus 2. And so my two solutions would be 8 and 2. All right, double check to make sure neither of these cause an extraneous solution. So if I plug 2 back in, those are good. If I plug 8 back in, that's fine. So now I have 2 solutions to that equation. What I want to do is go through one more problem, but I'd like to go through, actually I'm going to go through 2 more problems, but I'd like to go through a couple examples that are not on the sheet. So if you want to grab a sheet of paper, and then that way we can go over a couple more problems. All right, so I'm going to grab, so I wanted to go over one that was a little bit more challenging, just so you guys can see kind of a little bit more a difficult level of question. So let's start with this rational. So 4x over x squared minus 9, x minus 1 over x squared minus 6x plus 9, and then add 2 over x plus 3. So obviously this one's a little bit more involved. So what your first rule of thumb is to go ahead and factor everything. So let's factor that denominator. Let's factor this one. And then that one obviously doesn't need to be factored. It's already in simplest form. So now what we're going to do is we're going to go ahead and scale up this whole equation by the common denominator. So we have x minus 3, x plus 3, x minus 3, x minus 3, and then x plus 3 is all of my denominators. So my common denominator is I have an x minus 3, but notice how this one has 2 of them, right? So this is like saying x minus 3 squared. So because this is the same factor, you need to have, in order to figure out my common denominator, I need the highest power. So I need to have x minus 3 basically twice. So if you want to write it as x minus 3 times x minus 3, or you can write it as x minus 3 squared. And then if you notice, then a couple of the other ones have the x plus 3, so we need to add that in there as well. All right, so let's scale everything up. So for here, the x minus 3 and the x plus 3 would cancel. So all I'd be left with is another x minus 3. And then here, the 2x minus 3's would cancel. So I'd be left with x plus 3. And then this one, I'd be left with the x minus 3. And we can write it as x minus 3 squared, or you can write it as 2 times x minus 3, x minus 3. Okay, let's go ahead, now that we got rid of all the fractions, let's go ahead and distribute and simplify. All right. So I just went ahead and distributed through the parentheses here, and I FOILed here. I went ahead and distributed the x minus 3 times x minus 3, and now I'm going to multiply everything by 2. Oops, this is a squared. I forgot my squared. Okay, now that I have everything kind of, all of the parentheses taken care of, let's go ahead and combine some like terms. Obviously a little bit more involved in this one, so I'm going to have 2x squared and x squared gives me 3x squared. Positive 2x and negative 12x give me negative 10x, and 18 minus 3, excuse me, is 15. You can still tell that it's quadratic, so let's go ahead and set it equal to 0. I'm going to subtract 3x from this side, so that way it remains positive. I'm going to add 10x, and I'm going to subtract 15. So it looks like that. So I just moved all of these, excuse me, I moved all of these over to the left side. All right, let's go ahead and factor. So I get x minus 5 and x plus 3. So numbers that multiply to negative 15 but add to negative 2. So my solutions are x equals 5 and x equals negative 3. All right, so we do have to go back up here and check our solutions. Does 5 cause my denominator to be 0? And I don't see where it would, so it looks like 5 is a good answer, so we're going to go ahead and keep that one. Does negative 3 cause my denominator to be 0? Any of them, to be honest with you. And the answer is yes, because if I plug in negative 3 here, this gives me 0, and 0 times anything is 0. And then, of course, if I plug negative 3 in over here, I get 0 as well, which means that this is an extraneous solution. So this one right here is an extraneous solution. So this would be like the kind of the graph that you're going to have a vertical asymptote in. All right, the last thing I would like to do is chat with you about how to determine and find inverses of rational functions. So we've talked a lot about this in our exponentials and logs unit, if you remember that. And so this one, we're finding and determining inverses. So we're just going to type a quick note here. So let's go ahead and kind of chat a little bit about how to do this. So let me give you a function. So let's go with f of x equals, let's just do something kind of basic. Let's go 7 over x plus 5. So let's go ahead and start by graphing it. Okay, so one of the ways that we can determine if this function is going to be, if the original equation is a function, which obviously it is since we're kind of calling it a function, but if the inverse is a function, is we would need to graph it. So if you notice here, we can kind of do the same thing that when we graphed functions before. Let's find our vertical asymptote, which is going to be at negative 5 if we set our denominator equal to 0. In this one, if we set our numerator equal to 0, we don't really get anything, right? So that means there are no x-intercepts. And then when the numerator degree is 0 and the denominator degree is 1, we have a horizontal asymptote at 0. So this is kind of going to be where my graph is going to kind of lie at. Let's go ahead and plug in some values here. Since this is negative 5, if I plug in, let's see here. So let's think of x and y values, right? So let's plug in negative 4. We can't plug in negative 5 because that's an asymptote. If I plug in negative 4, I get 7 over 1, which is 7. So my graph is going to be up here. Let's see what happens when I plug in 0. So if I plug in 0, I get 7 over 5. So that's about, what, 1 2/5? So that's 1 point, so about almost a little less than 1.5. So maybe about right here. So here's what I'm getting from this. If I get a couple points at least, I can get a feel for how my graph is going to look. So it's obviously in this quadrant up here, and it's passing through those 2 points, has to approach my asymptotes. All right, I'm going to guess that my other one is down here, but let's go ahead and sketch a couple extra points just to be sure. So, I don't know, let's pick like negative 6, for example. So negative 6, I would get 7 over negative 1, which is negative 7. So 1, 2, 4, 5, 6, 7. So let's go -6 and -7. So that one's here. Let's plug in, let's see here. We did -6, -7, -8. We could do -7. So 7 divided by, that'd be negative. So 7 over -2 would be like -3.5. So at -7, it'd be like -3.5. So about right here. All right, that gives us a pretty good indication of what our graph is going to look like. So it's going to approach the asymptote. It's going to pass through those points. And there we go. All right, so that's how we're sketching our graph, just kind of by hand. Obviously, you can use a graphing calculator as well, but I thought it would be helpful to demonstrate how to go ahead and do this by hand. All right, last but not least, in order for us to determine whether or not this inverse, so the inverse of this function, if the inverse of this function is indeed a function, you have to pass something called the horizontal line test. So you might remember the vertical line test. So the vertical line test meant that if you can draw a vertical line and it only hits at most one point, that means the graph is a function. So a horizontal line test is kind of the same way. So if you can draw a horizontal line and it only hits one point at a max, that means the inverse of this graph will be a function. And so if I did this one, even though it kind of looks like this is a straight line, this is approaching this asymptote, so is this. So all these points are really close together, but they're not like in a straight line here. So this passes the horizontal line test. So what this tells me is the inverse is a function. So a lot of times the question will say something like, is the inverse a function? And as long as it passes the horizontal line test, it is. So that's one way of doing this. Another way is kind of using our idea of how to find an inverse. So to find an inverse, let's start with our equation. So I'm going to change this to y equals instead of f of x equals. You would do this the same way we did this in the previous units. You would switch x and y. Okay. And then you would solve for y. So what we're going to do here, since this is a proportion, we're going to go ahead and cross multiply. And then since I'm solving for y, let's go ahead and get rid of the x. So I'm going to divide both sides by x. And then I'm going to go ahead and get y by itself by going ahead and subtracting 5. So the inverse of our function is still a rational function. This is what I started with. This is my inverse function. And so that's how you find an inverse of a function. All right, that's all we needed to do. I wanted to at least give you a couple examples of like how to do the whole inverse thing. There's not a ton of that on here, but at least gives you an introduction. Try the stuff that's online. If you have questions, bring them to class. All right, that's it for now.